Thank you for the introduction. So I would like to thank Corinne Pasquier for the invitation to this event and to thank Manutech-SLEIGHT for this event too, with a special mention to Cecilia Chen for the logistics around it. I would like to start this talk with a confirmation about our activities in Opto. So we are expert in imaging solution around the hardware and the software between the input, so the object, and the labeling to deliver perfect data, so many times the images and sometimes the classification. I wanted to start with some generalities too around the quality control for us with vision and to how we integrate machine learning in our projects. So our point of view where it's to cut a project in 3 phases with machine learning. So the first phase is to integrate to choose the setup, in fact, with the hardware and the software first, and to decide how to manage data. So the IT infrastructure too. The second step, the second phase, where to decide 4 steps around machine learning. So the main topic today, and the third phase is the deployment, so to integrate the digital imaging solution in a box with the prediction software to make data and to integrate in IT infrastructure. So I start a little bit quick to describe this step. The digital imaging for us, it's to translate imaging object from reality space to machine space in machine language, so in image and in pictures. So when you have chosen this digital imaging solution, you can put in a learning step, like a loop of digitalization to generate data and to transform a first set of objects in images and in data to reveal, in fact, anomalies, artifacts. And then you get first rules. After the modeling, it's the goal to define the type of a problem and to choose what is the type exactly to glue to the type of data. If you have a 1 class problem or 2 class or 10 class, and there you have some visualization tool to decide if you have a good problem. Pardon, je crois que c'est Julien, j'ai des retours. Pardon. You can cut your microphone, please. The third step in our machine learning pipeline, it's the prediction step to apply the second loop of digitalization with the same recipe of digital imaging and the model decided just before. So to get some score and some response of a new set of objects. And the goal of this prediction is to compare the prediction with reality, so the knowledge you have already from the object. It's the most important step for us in industry because it's there we can compare the quality of the machine learning solution we decide, in fact. And we have the true positive and the true negative, like the normal way to recognize bad and good part in good part and bad part in bad part. But in fact, many times the level of quality you want in industry, it's decided there because sometimes you want 0 defect in your production. So you need to choose a threshold to eliminate all true negative and false negative too. So you have 2 scores, and the goal after to have all elements from digital imaging, modeling, and so high level quality of machine learning solution is to integrate this solution in one box. So in industry, we don't like black box because you have 2 points. In fact, the first black box, you are completely blind to control the process, and you want to put a new part inside and to get a response, yes, but you want to explain, in fact, the behavior of your box. And secondly, in fact, we have a GPD, so the regulation of data protection. You need to explain. You have to explain the behavior or your classification model, in fact, in your box to avoid a bad case, in fact, especially in a critical area like aeronautic or medical. So, and the goal there in machine learning is to decide a perfect format to Industry 4.0 to connect all elements in the same format and to make a loop between all elements. So our feedback, in fact, it's there. I try to integrate all almost all company we can see today and tomorrow, except the MicroLight 3D, because I think MicroLight 3D it's more expect more risk answer from you than us. So Opto, it's more like the beginning or beginning partner to identify what is the right data to generate from reality to machine space. So we have two levels with the COP. In fact, it's the first software services to translate knowledge from we have from expert to digital space. And the second level, it's more imaging solution with imaging module and software to translate object in image and in features. My top point of view is near vision is the expert to transform Y and images in model and perfect neural network to as classification software to make quality control, if you want. And TMR for me, it's more the perfect partner to get the machine with inside. So you put the glass product and you got the response and the product, the good product and the bad product directly in the machine. So another point of view of our activities could be there. And I wanted to show you another point of view to the industrial dream, in fact. Many companies, no expert in machine learning, expect one type of product, in fact, to get a scanner like this. For industrial product, you have a new product without knowledge and purely non-supervised scanner, and you got a response like one universal response with the defect and the type of defect, the criticity. And in fact, in reality, you have many parameters before for the production, for making the product. You have a limited batch, a volume of batch from one production, from one factory. And for this product, you have one shape. You need to define the digital imaging for it. You need to define the type of machine learning. So the model, 1 class, 2 class, 10 class. And you need to define the format of data after, how to store, to get a signature one archive of the product, depending on your area. In medical field, you need to store data during at least 15 years. So the size of data could be important. And the goal of Industry 4.0 is to get new mode of communication and to connect all machines to make something more universal, if you want. Some difficulties we have, in fact, in industry is we got many times when we start the project of machine learning, we got a small batch of data. When we have many parts, we have 100 parts. And we have a problem of the knowledge of the company about deep learning, because they know the performance of deep learning. But in deep learning, you need at least 10,000 points to train, in fact, the model. So in our case, with 100 points, we have not enough, and we can start to learn, but could be interesting to observe the representativeness, in fact, because if you learn 2 parts good for 10 parts with defect, depending your model, you can learn the ratio of between good and bad parts. And indeed, if you want to recognize only 2 parts for 10 parts, 2 good parts for 10 bad parts in production, it's a real problem for the production, because you lose money and you make purely waste, in fact. So at this step, we need to be sure we have a good representativeness of the set of a production in the learning set. And secondly, another difficulty is to be sure we have the right data in the learning set. So good part, it's real good part, and bad part, it's real bad part. So from Opto, we worked at this level to be sure we have a right translation from reality to machine space. Secondly, after to get a first set, in fact, to learn, to train, we have to offer a warranty. We have enough features to identify the good part and the bad part. And our point of view is to work based on good parts to identify where we have some variabilities, and we have the convex hull of conformity. In fact, we want to identify more of the conformity, because like that, it's easier for us to say, okay, this part, it's out of the convex hull, so it have a defect. And after we worked according to the direction, in fact, of the deformation of the feature to identify some class and some defect class, in fact. So there, the difficulty to identify enough feature to see all defects, because the definition of defect and anomalies before, anomalies, it's something we don't know a priori. So we need to learn a behavior with enough feature to describe all behavior and to recognize something is different than before. The difficulty in the industry, when you have some million of production, some million part production, is many times you have one defect based on one feature with some small variation. So we have to learn with variabilities, but the variabilities of the critical features are very small, in fact. So yeah, for Opto, in fact, we propose a tool to make the learning set more robust. I can jump a little bit fastly, because normally, yeah, I have my time there. Maybe it could be enough, I think, to start this week. If you have some question about this, I can answer on the chat or on Gather-Tool, or during this week. If I made, if you need my mail.
Thank you very much, Simon. If you have any question, you can use chat box or just yes. Mark, you have a question?
Yes. Can you hear me?
Yes.
Okay, thank you very much for your presentation. I have a comment. Maybe you will be interested in the session tomorrow morning about anomaly detection, because we'll have a specific session on how to detect anomalies and how to address the specific problems of having imbalanced data sets, because it's the problem in anomaly detection. You have many examples without any problems.
Okay.
And fortunately, I would say, but because of this imbalance ratio, important imbalance ratio in the data set, we are facing problems. And tomorrow morning, we will talk a lot about this during the session given by Rémi and Monet. So this was a comment. I have a question about the method you are using. If I understood well, you said that one of your main objectives is to check that the training examples are representative of the production distribution. I mean that sometimes there is a shift between what you are learning from and what you are going to use when you will deploy the model. And actually, it's very similar to the problem of transfer learning. I don't know if you know this topic when we assume that there is a shift of distributions between the training and test time. So I would like to know if you are using specific methods coming from transfer learning and domain adaptation to address these problems.
Okay. Yeah. In fact, the difficulty we have in industry is to get some real data, in fact, from before to make the transfer learning. So we start many times from zero, jump a little bit faster, but we try to work with experts to be sure we have the right response. Could be maybe the right example could be there. To get the right response about part and to be sure the part is good, because if we learn some bias data, we change in fact the quality of modeling after. So we have to be sure the good part is the good part, the bad part is the bad part, and if we have some ambiguity, we eliminate this part from the learning in the first time. So we can do some simulation too. But in fact, it's some time in an industry. The time it's some money too, and the time to keep to get this response from controller. It's many times it's not a time take account by industry. They think they put the object in the machine and they got the response directly, and we have some time to learn with the controller. If you have a 100 part with 5 minutes by part with one controller, it's already 6 hours. So 6 hours is 1 day. You have to pay 1 day. So free controller, 3 days, 1 week, and so 1 week and more with a price of controller around 1,000 euros by day. So it's 5,000 euros and more. So it's purely a question of money too. Because it's a time and you need to be sure this time it's okay not to lose after. It's the difficulty. It's there for us. We already trained some model with TensorFlow before to make some small transfer learning from 10 to 10, by example, to configure. But we have to be sure of the quality of data before the machine learning pipeline. Because jump a little bit between my slides, but at the right side you have some statistic about the quality of object and the evaluation of object, but we can get the same for inspector and for the machine too. And the metrics for industrial company, it's the return of investment, So it's the score between controller and machine. So if a controller is performed to 19% and the machine is performed to 17%, we have no interest to go with a machine. But if, like the deep learning mentioned, we have some performance around 95, 96, 98% of good quality with a machine, and the controller stay at 19%. We have directly the score, the gain, in fact, with a machine to apply some vision, artificial vision. So we know we have some tools ready to apply for anomaly detection, but each case is different because you have some specular lighting, you have some different color, some different sensitivity, and in fact, with all parameters, we have to find the right compromise, in fact, to make the quality control and after the process control too, because the goal is to identify before the event if you have some tool break and work. And I don't know if I could respond for you, but I hope it's a good introduction for tomorrow morning about anomaly detection. So.
Okay, thank you very much for your answer.
Thank you, Simon. Thank you
Thank
for
you.
the thanks. I think there are no
I don't see the question.
I think the time is up, but for the audience, you can meet Simon on the Gathernote platform and discuss with him. Thank you. Thank you so much, Simon.